And we are live. Ladies and gentlemen, we are live. We are back. Can you believe it? We're here. I don't know. I don't know what's going on anymore. Let me do that real quick. There we go. But yeah, what a wonderful snowy day that it is. I see that I have 7 of you so far, and people are proclaiming themselves present and here and things of that nature. Thank you for that. I appreciate that. I appreciate your presence. I have been because I this is exactly what happened when you guys were virtual for 2 weeks. Like I was just stuck here, like not here, but like in my classroom talking to nobody. And now I'm here and it feels like I'm talking to nobody. Well, but the only difference is my daughter is knocking at the door, or was knocking at the door earlier or something like that. Here, I'm going to show you some pictures. I gotta find them first. On Facebook. There we go. Let's see here. Yes, I think this will do it. So my here we go. Hold on. Website. There we go. Look at that. There's my daughter. Can you all see my daughter? Look how stinking cute she is. This was her 2 years ago, and she doesn't really remember that all too much. And then this is yesterday, and that's actually her knocking at my door right now. And there she is right there, being all cute. And there's my son, being all awesome. And there's my daughter, eating it, just taking a dive. She didn't care. Yeah, we live next to a golf course, so there's like hills behind us, like bunkers and whatnot. But of course, and then there's our backyard and stuff like that. It was yesterday. That's just something else entirely. I should get off of that. But yeah, that's my family. Top down. There we go. Yesterday, out in the snow. It was just one of those things. Anyway, but we're back. We're back and we're back and we're back and we're back. Oh my word. Oh, it is such a different feeling being at home. I want to be in my classroom. Today, we will be continuing with Chapter 6. We will be continuing with a bunch of the information that we've been doing. I need to print this out so that I can use this today. Here we go. In your Google Classroom, I am going to be posting a PDF file of the worksheets that we are going to be working on. Let me just find the right ones here. My drive, Algebra 2. Let's find the right ones here. There we go. There are they. Boom and boom. Insert PDFs for today. Come on. PDFs for today. Type it out. PDFs for today. My keyboard is not working. Today. Post. There we go. So if y'all check your Google Classroom stream right now, you will find that there were 2 PDFs attached to a post, and I'm going to be working off of those for the next several class periods. The one I'm going to be focusing on mainly today is the 6.5 side. Now, again, you have the PDF just in case, because obviously you may not be able to see exactly what I'm seeing right here with my worksheet. But we will get this thing done. I mean, not the whole thing. Oh man, these things didn't print. Whatever. See, this is what happens when I try to print stuff from home. That's terrible looking. Whatever. The examples that I want to do are still there. So that's all that matters. The examples that I want to do are still here. It's going to be nice. So, what I'm going to need from you, if you do not already have them out, are for those notebooks to be out. and open. Oh man, my camera froze on me. Let's fix this up, shall we? Close that. Close that. Reattach that. Oh, my wife asked me if I wanted a pancake delivery. Do any of you guys want a pancake delivery? I don't know. I mean, I don't want any, but do you guys want any? It's up to you. Man, I had this issue with the camera earlier today. The camera decided to basically not work for a few minutes, and I was able to fix it. Thankfully. But I had to close a few things out and restart something, so it'll just take me a moment. But yeah, if you haven't already left a comment in the chat, please, please do so. Come on, thing. Boom. Come on, phone, do your thing. Searching for IVCam PC. Yeah. See, what I'm trying to do is I'm trying to connect my phone, which I'm using as the downcam webcam. Usually I do this in school using the Elmo camera. But until then, I'm kind of stuck. It happened to me first period, so if you'll bear with me, it won't be that bad. Ooh, what's that? No, I don't want to enter in an IP address. Do I have to restart this thing? I don't want to restart this thing. Anyway, I do have a few backup plans as a just in case, but we'll see how that goes. Okay, good. Okay, all right. So hold on. I went to the wrong thing right here for the phone. Live streaming, sound capture. Let's see if this works. Nope, that totally did not work. There it goes. Good. Disconnected. Reconnected. Change it to that thing. And it worked. Excellent. Thank you for your patience. Thank you for your patience with the technical difficulties. This is what happens when I try to use my phone as a webcam. You know, issues. Maybe I just need a new phone. I don't know. I'm working off of a Galaxy 7, so whatever. Okay. So I am going to be picking problems off of the worksheet that I posted to the Google Classroom. So what I'm going to ask of all of you. Did it freeze? Oh, don't even start with me. It froze again. Golly. Did you freeze? No. 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 It didn't freeze there. It says it froze there. Hold on. Let's see if the... Okay, that should work. Let me double check. Again, I apologize with how ridiculous this seems. Okay, good. Stupid technical difficulties. Let me start again. If you do not already have them out, I'm going to need those notebooks out and open. Let's call this simplifying radicals. Now, before we had this week of midterms, we were working a little bit with simplifying radicals. We did some basics, but now we have to deep dive it. This chapter, chapter 6, is going to contain some amazing problems in the coming weeks. But we unfortunately are not going to get to those problems soon, but we need to get to them via these problems, simplifying radicals. So let's just start very simply with number 1, and I'll show you exactly what I'm referring to. Example number 1, the square root of 540. Now, 540 is not a perfect square. If you were to take the square root of 540, you would absolutely get a decimal. That is not what this problem wants. This is not what this problem needs. What this problem needs is for you to simplify it down as far as it could possibly go. When you hear the word simplifying, you typically think of like simplifying fractions, so to speak. Simplifying fractions like the fraction 2 over 4. 2 over 4. Well, you're not going to leave the answer as 2 over 4. You're going to simplify that 2 over 4 to be a 1 over 2. And that would be the simplified answer. The reason why that's important is because, well, you might get an answer of 2 over 4. And this person might get an answer of 3 over 6. And I might get an answer of 12 over 24. But because they all simplify to the same answer, we know that we all got the same answer. Simplifying allows for consistency. Simplifying allows for one definitive answer to be written. The square root of 540 is not a perfect square. Now, I do apologize because, again, I don't have my regular calculator. I'm going to have to use this calculator, and it's not the best to, visibly see or whatever, but we're going to do our best with what we got. Move this over just a tiny bit. There we go. Good, good, good. So I'm going to take the number 540, and let's just divide it by 2. Let me divide it by 2 again. Oh, okay. I divided it by 2 twice. All right. Can I divide by 3? Sweet. Can I divide by 3 again? Sweet. Can I divide by 3 again? Sweet. I did it 3 times. And then I got a 5. What that means is this. I was able to break this 540 up to its prime factorization of 2 times 2 times 3 times 3 times 3 times 5. It doesn't take that much digging to find that out. It really doesn't. It's literally just dividing it by numbers to kind of figure out, like, okay, what do I got to do? I mean, you could literally do like a number tree if you wanted to, where it's like, okay, I'm going to divide it by 10, and divide it by 9, and then, okay, well, the 10 and the 9 and the 6 you would have to break up. The 10 would turn into a 2 and a 5, the 9 would turn into a 3 and a 3, and the 6 would turn into a 2 and a 3. And ultimately, you'd end up right here, again. That's what you want to happen. That's exactly what you want to happen. But now here's the idea of simplifying. It is a square root. And because it is a square root, the only thing that is allowed to escape from a square root is a perfect square. And because of that, 2 times 2 is a perfect square, because that's 4. We'll put those together. Oh, look, 3 times 3 is a perfect square. Let me put those 2 together. This 3, what do I do with that 3? Well, it's not a perfect square. 5 is not a perfect square. Putting them together is not a perfect square. They're stuck. There are certain terms that are going to be stuck, and there are going to be certain terms that are allowed to escape. But what ends up happening is, well, you have the square root of 4, and the square root of 9, and the square root of, well, 3 times 5, let's make it a 15. And the reason why that's helpful, because now, well, look, square root of 4 is 2. Square root of 9 is 3. Square root of 15 is just stuck. And ultimately, the final simplified problem is 6 times the square root of 15. There are faster ways of doing this, and I'm going to show you one of those faster ways in a moment. But this is the nuts and bolts of what we're going to be focusing on. You don't have to take the shortcut. You don't have to. You don't. You'll end up at the same answer, maybe with more steps, but you just don't have to take the shortcut. Watch. If you know anything about the number 540, you could divide it by a couple of things. You could try to guess and check what kind of perfect squares you can dig out of it. And ultimately, you'd be like, okay, 540 divided by 36. 36 is a perfect square. Oh, look, 36 times 15. Oh, there goes my pen. So I could break this thing up to be the square root of 36 times the square root of 15, which I know the square root of 36. It's just 6 root 15. There's a shortcut. I don't know that many people who always figure out the shortcut. I don't know many people who always figure out the shortcut. I know some people who figure out the shortcut here and there, but I don't know that many people that do it all the time. If you can figure out the shortcut, good for you. I asked my period 3A class on Friday. I said, okay, some people take the shortcut, some people take the long route. How do you get to Tom's River? And they're like, what? And I'm like, how do you get to Tom's River? And they're like, well, I take the Parkway. Okay, what if the Parkway's closed? I just take Route 9. Okay, what if Route 9's closed? Then you're out of luck. No, you're not. There's always more than one way to get there. You could take the back roads if you know how to do that. You could walk if you knew how to do that. If you knew how to walk. But my point being is clearly there are going to be some ways that are shorter than others. Maybe the shortcut here is the Parkway, but maybe you're somebody who's a new driver and you don't feel comfortable or safe on the Parkway. And as a result, you decided to take Route 9 because that's what you're more comfortable with. And Route 9 would be taking this route to get to the answer. What have you. There's always more than one way to get to Tom's River. There's always more than one way to solve a math problem. Some ways are faster than others. I'm looking at number 2 on that PDF. Number 2 on that PDF is now the cubed root of negative 432. Now, something you got to know. This is a cube root, meaning the only way you're escaping a cubed root is if you are a perfect cube. Okay. 432. I have no idea if 432 is a perfect cube, not to mention it's negative. So what do I do with that negative? Hold on. Let's check a couple things. First, you do have a cube root function in your calculator. You do. You hit math, that little 3, root, it's a cube root. Clearly, 432 is not a perfect cube. It's not. But the cube root of negative 1 works. This is something that we have to recognize. The reason why negative 1 is a perfect cube is because, well, negative 1 times negative 1 times negative 1 is negative 1. It's one of those things that we have to recognize and we have to remember and utilize when the time shows up. And this is one of those times. You are allowed to take the odd root of a negative. Let me repeat that. You are allowed to take the odd root of a negative. You are. It's great. Beyond that, let me take this 432 and let me break this 432 up. Because I don't know what to do. Let me just try to see if I can divide it by junk. Divide it by 2. Ooh, I can do it again. Ooh, I can do it again. Ooh, I can do it again. So 1, 2, 3, 4. I did it 4 times. And then there's a 27. 1, 2, 3. Okay. Negative 1 times 2 times 2 times 2 times 2 times 3 times 3 times 3. Now, there's definitely an easier way to do this problem. And I'm going to show you an easier way to do the next problem, of course. after I give you an opportunity to try it on your own. But this problem, the reason why I wrote it all out like this, first of all, I can take the cube root of -1. As I just demonstrated on the calculator, it's -1. But in order to escape a cube root, you must be a perfect cube. As a result, there's a perfect cube. 2 times 2 times 2 is indeed a perfect cube. It's 8. And then 3 times 3 times 3 is 27. That's also a perfect cube. Now this -1, like I said, that -1 is just a special case. I'm just going to bring that one out. What about this 2? Sucks to be that 2. You're out of luck. Let's see what happens. So this would become a -1. The cubed root of this would become a 2. The cubed root of this would become a 3. And this 2, I'm sorry, is out of luck. It is not allowed to escape. Ultimately, this would become -6 times the cube root of 2. This is the simplified answer. This works. Again, the reason this is a means to an end. The simplification that we're doing now is going to apply to what we're going to be doing later on in this chapter. It absolutely will. It's going to be amazing. For me, not for you. It's going to be amazing for me. Now I can show you, actually prove it to you. Here, check this out. We did before the cubed root of -432. And I got that decimal. I could also do -6 times the cube root of 2. Clearly the exact same decimal. The difference being, the answer that I have at the bottom is simplified. That is what we need to do. We need to simplify our answers. So what I'm going to ask you to do, I'm going to give you a moment, like a minute or so, and I'm going to be right back because I got to go bring my daughter a stuffed animal. But I'm going to have you do number 3. Number 3 is the cubed root of 128. No negatives to deal with, no tricks. See if you can do this on your own. I'm going to give you a minute, and of course I'm going to show you how to do it, but I'm going to give you a minute to try it on your own. So do that. I'll come back and review this problem with you, and then I'm going to show you a special case. I'll be right back. Yeah, duh. Okay. Sorry, I took a little detour to eat one of those pancakes. My wife said that the pancakes are ready for whoever wants them. So, I mean, if you guys want to stop by for pancakes, that's on you. They're really good. Just saying. Homemade. Anyway, back to this. 128. It doesn't take that much digging to figure out that 128 can be divided by 2 over and over and over again. In fact, it can be divided by 2 7 times. It is 2 to the 7th power. So I'm going to take a little bit of a shortcut on this thing. Actually, no. You know what? I'll take the shortcut over there in a minute. Let me do it the long way first. Here's the long way. 2 times 2 times 2 times 2 times 2 times 2 times 2. There are 7 2's there. Because, as we said before, 2 to the 7th power is 128. But this is a cube root, meaning the only way you escape a cube root is if you are a perfect cube. There's a perfect cube. There's a perfect cube. Well, this would be the cube root of that, which is 2, the cube root of that, which is 2, and this is just the cube root of 2 left behind. This becomes 4 times the third root of 2. That's just one way of looking at it. There's more than one way to do this problem. Let me show you a little shortcut. The cube root of 128 is in reality the cubed root of 2 to the 7th power. 2 to the 7th power. Now, 2 to the 7th power, I could break it up like this. I could break it up like that. Because, well, 2 cubed and 2 cubed and 2 to the 1st is 2 to the 7th when you add the exponents together. The cube root of this 2 cubed, the cube root of this 2 cubed produces these 2's. And then this 2 to the 1st is unfortunately left behind. Another way of kind of thinking about the shortcut, besides doing that, because I wanted to show you an actual shortcut, is this. A cube root is nothing more than a 1/3 power. It's a 1/3 power. That's what a cube root is, power over root. You can apply this 1/3 power to both of those exponents, and you end up with, well, 6 times 1/3 is 2, so that would be 2 squared times 2 to the 1/3, which is really the cube root of 2. And 2 squared is just 4. There's always more than one way to look at this problem. Personally, I would be very happy if everyone just kind of stuck with this. Let me show you an example that's not on the worksheet. It's actually a bit of debate over this problem. The 4th root of 4. There's a bit of debate over this problem as to, well, how are we supposed to know we're done? When you look at this problem, you initially think, okay, 4th root, meaning in order to escape a 4th root, you need to be a 4th power. You need to be a perfect 4th power. 4 is not a perfect 4th power. 4, when you break it down, is nothing more than 2 times 2. You can't do, nothing escapes. You can't do anything. That's just 2 squared. Look, it's just the 4th root of 2 squared. You can't do anything. So what do you, I guess it's simplified. Using the basic rules that I have been teaching you, yes, for the most part, the fourth root of 4 could be considered simplified. But it's not. Again, mathematicians are kind of split over this. I know what the correct answer is because I'm always right. When you have a radical like this, a root, you can think of a fractional exponent in the form of power over root. Power over root. Power over root. It's a fourth root, it's a second power. The way we find that, number one, you do the same factorization as we did before. It's really 2 squared. Nothing escapes the fourth root at this point. Nothing escapes. So instead, I convert to a fractional exponent. And then realize, oh, snap. This is really 2 to the 1/2 power. Because 2/4 simplifies. And if I were to convert it back, this would really be the square root of 2. Now, on a calculator, this should make somewhat sense. Check this out. The fourth root of 4 is this decimal. The square root of 2 is obviously the same decimal. If I were to take that decimal and square it, it gives me 2. If I were to take that decimal, and raise it to the 4th power, it would give me 4. It makes sense that these two concepts would be equal to one another in that sense. Very strange idea. It's a similar notion. It's a similar notion to the idea that 4 squared is 16 and 2 to the 4th is also 16. It's a similar notion. Powers of 2. But that would actually be the simplified version. You're going to need to know your perfect cubes. You can obviously use a calculator to get a lot of that stuff done for you, but you're going to need to know your perfect cubes. Okay. I have 2 more problems I want to do today. One of them is going to be a simple problem, and then one of them is going to be a not so simple problem. This is number 11 off of the worksheet. Square root of 11 over 9. You are allowed to do the following step. You're totally allowed to do that. You are. You absolutely are. Why? Well, multiplication and division. The reason why a lot of these steps can be taken is because of multiplication and division. In fact, a lot of the rules that, and this is one of the first problems I showed you today, a lot of these rules rely heavily on multiplication. Oh, it's upside down. Rely heavily on multiplication, division, separating these terms. Because multiplication or division is separating all of these terms, come on, you are allowed to do a lot of these steps. Division is separating this one. And because division is separating this one, you are absolutely allowed to separate those 2 terms from each other. What? Hold on one second. I just got to read something here. Haha, nice. Sorry, I was just reading a something, an email that I got. I just thought it was cool that I got it. So anyway, back to this. Now, why this is important? Well, 11 doesn't do anything, but the square root of 9 is 3. Yeah. It's a very straightforward problem. As long as you recognize the fact that you're allowed to split them up with multiplication division separating the two terms. It's really nice. Now, there's something extra here. And that something extra won't pop up till the next problem. The next problem, now, I know what time it is. I know how much time I have left. And I will tell you that the next problem is the last problem we're doing today. But this last problem is going to be a doozy. This last problem is going to be very important. This last problem is going to be a good one. I'm hyping this up because I need you to recognize the importance of this last problem. And for those who may be like, I'm skipping out early, I'm going to go play in the snow that's now all ice and water, whatever. No, you need to see this example. You need to know how this example works. This is going to take some time. The cube root of 216 divided by 24. Now, I'm going to break this up to be the cube root of 216 over the cubed root of 24. This is number 12 on the worksheet, by the way. Question. Now, don't answer this in the chat. Just kind of answer this to yourself. What is the number of the devil? Most people would say it's Ms. Markey, it's 666. Why did you say 666 and not 666? He says South Africa. Why is he saying South Africa? That's weird. But anyway. Yeah, a lot of people would say 666 and they would not say 666. Why? Why would you not say 666? I don't know. I guess I just always heard it as 666. Well, there are some people who believe that the reason why it pops up as 666 is not because it's the number 666, but because it's 6 times 6 times 6, which is 216. That's the reason why I bring that up. 216 is a perfect cube. Now, what actually is the number? I don't know. Just, that's not important at the moment. But 216 is important at the moment. 216 is 6 cubed. It's a perfect cube. 24 is not a perfect cube. It's not. However, 24 does hide a perfect cube. Check this out. This is the cubed root of 6 cubed, which we will take care of in a moment. And on the bottom of the fraction is the cubed root of 8 times the cubed root of 3. The reason why I did 8 and 3 is because, well, 8 times 3 is 24, and 8 is a perfect cube. 2 times 2 times 2. So this becomes, well, 6 over 2 third root of 3. Now I could simplify this a little bit more. I could simplify this a tiny bit more, and I could get 3 over third root of 3. Because 6 divided by 2. However, this answer is not satisfactory. This answer is not acceptable. The reason why this answer is not acceptable, the reason why I cannot allow this to happen is because of the simplification rules in mathematics. There are certain procedures that have been decided upon. And one of those procedures is I cannot leave a radical in the denominator of my fraction. I can't. I am not allowed. We must rationalize the denominator. We must rationalize the denominator. You cannot leave a radical in the denominator of a fraction. Now I'm going to show you how to do that in a moment. It seems so straightforward up to this point. It's like, okay, split this thing up the way we did the previous problem. 216 is a perfect cube. I could break up the 24 to be 8 and 3 because 8's a perfect cube. The cube root of 216 is 6. The cube root of 8 is 2. This 3 is left behind. 6 divided by 3 is 3 over 1. It seems so straightforward. But we must rationalize the denominator. This is what makes this problem a bit more challenging. So we don't have the answer quite yet. In order to rationalize the denominator, this is something that we're going to be getting practice with as time goes on. This is the first time you may be seeing this. But in order to rationalize the denominator, we need to force the bottom of that fraction to be a perfect power. Now, it's a cube root, so in order for that cube root to cancel out, we need a perfect cube. We need to force a perfect cube, in this case, to cancel out that radical. How do we do that? Listen very carefully. I am going to multiply this fraction by 1. You've done this in the past. You've multiplied stuff by 1. What happens when you multiply by 1? Mr. Markey, nothing happens when you multiply by 1. Yeah, I know. But remember back in middle school when you had to find like common denominators and all that fun stuff? Common denominators. You had to multiply by like, I got to change this denominator, so I'm going to multiply by like 2 over 2 or 7 over 7. You multiplied by 1 in order to change the way the fraction looked. And that's exactly what I'm about to do right here. I'm going to multiply by 1. There, I multiplied by 1. Well, where the heck did that come from? This is why I hate math. No, bear with me. Bear with me. First, we agree on one thing. Cubed root of this number divided by the cube root of this number. If you divide those two, you get 1. Because anything divided by itself is 1. I hope we can agree that I multiplied by 1. And the reason why that's important is because I don't want to change the value of this fraction. Second, I hope we can agree that the only way that this cubed root is going to cancel out is if what is underneath is a perfect cube. Let me repeat. The only way this cube root is going to cancel out is if what is underneath is a perfect cube. And right now it's not a perfect cube. But I can force it to be a perfect cube. This is how I'm going to force it. Multiplying these two denominators together, I can bring those two radicals together into a single radical. And if I bring them together, I would have 3 times 3 times 3, which would be a perfect cube. Ms. Margaret, this seems very elaborate. I know. First of all, on the top of the fraction, I'm just going to leave it as the cube root of 9 because 3 times 3 is 9. Nothing happens there. But on the bottom of the fraction, it's the cubed root of 3 times 3 times 3, which, as we have seen, can simplify. The cubed root of 27 is 3. The cubed root of this perfect cube is 3. So this becomes 3, third root of 9, over 3. What the heck? It's 3 divided by 3 there. I know. That is the simplified version of this problem. I want to recap exactly what I just did, and I will. I'm going to recap it. You're going to see exactly one step to the next in the logical progression. But let me just prove it to you here. Check this out. The cubed root of 216 divided by 24 is that crazy decimal. Interesting. The cubed root of 9 is that same crazy decimal. It's that same crazy decimal. It's really insane the way this thing works. Let me go back a little bit. Let me show you my logical progression here. First of all, 216 is a perfect cube. 24 is not. I can split this thing up to be the cube root of 216 over the cube root of 24. 216 is a perfect cube. Devil's number, 6 times 6 times 6. 24 is not a perfect cube, but I can break it up 8 and 3 because 8 is a perfect cube. The cube root of 216 is 6. The cube root of 8 is 2. And this cube root, sucks to be it, is still on the bottom of this fraction. 6 divided by 2, 3. And this cube root is still on the bottom of this fraction. But now the statement, we must rationalize the denominator. This radical is an irrational number. Irrational. And you are not allowed to have irrational numbers. You are not allowed to have radicals on the bottom of the fraction. So we must rationalize it. In order to rationalize it, I need to force a perfect power. And in order to force a perfect power, I'm going to multiply the fraction by 1. This right here is multiplying by 1 because anything divided by itself. The bottom of the fraction would become the cube root of 3 times 3 times 3, which would be, right here, that perfect cube power. On the top of the fraction, I'm just going to leave it as is for the time being. In fact, I'm just going to make that a 9 for simplicity's sake. This cube root of 3 times 3 times 3, as we've done from the beginning of this class period, would just give you a 3, forcing these 3's to cancel, leaving you with the cube root of 9, which is the simplified answer. We have to be able to simplify our answers. Now, what I just took you through was kind of the long, drawn-out way of doing things. There are shortcuts. There are definitely shortcuts. Let me just show you, actually, I did fib a little bit. I do want to show you one more short example. One more short example involving this concept. 1 over the square root of 2. 1 over the square root of 2. Can't have a radical in the denominator. Now, mind you, it's a square root. In order to cancel out that square root, you need a perfect square on the bottom. I'm going to force a perfect square by multiplying by 1. Right here, I multiplied by 1, not changing the value. On the bottom, it would become the square root of 2 times 2. Which the square root of 2 times 2? Well, it's the square root of 4, which is 2. That would actually be the simplified version of this original fraction. It is. It doesn't look as simplified. I know, but it is. Just marking, they don't even look the same. I know. Check this out. 1 divided by the square root of 2. Square root of 2 divided by 2. They're the exact same decimal. It's just that one is simplified because it does not have a radical in the denominator. All right. We are going to pick up with more practice and examples on Wednesday. I'm going to wrap up right here. I assume we will be back in my classroom on Wednesday. That's my hope. Although I do have a slightly better setup here. Yeah, why is this so not bright? Hold on. This is not as bright as I wanted it to be. I gotta charge that thing. Anyway, I hope you guys have a wonderful day. Go enjoy the snow. My superintendent said to, let you guys go a few minutes early so you can enjoy the weather outside. I said sarcastically. Sorry. It's been such a weird day. Anyway, I hope you guys are doing well. I'm going to sign off. And, yeah, have fun. We'll see you Wednesday.